So part of chapter 4 deals with what we call solutions because they have this calculation as well that you involve moles. Solutions is something that is going to show up in Chem 1. It's something that's going to show up in Chem 2. It's something that shows up in chemistry and any course you take. So you need to learn how to deal with it. It's not going away. So we'll define some wordings and all that, and there's some type of calculations towards the end. And then we have a lab next week on solutions that I think you'll like because you'll be working with Kool-Aid. Not that you can drink it. Let me put that out there right away because we don't drink or eat in the lab. And that Kool-Aid in the lab has been there for years, so I wouldn't even try to taste that. So, okay, let's just move on. So when you have a solution, that solution can be homogeneous or can be heterogeneous because it's going to be made of two different things. It's going to be made out of the solvent. It's going to be made of a solvent or a solute. The solvent is what dissolves the solute, and the solute is the solid that you're adding. So the solute tends to disappear. And it's not really disappearing, it's still there. Yeah, so when you have a solution, when you're mixing two things, where one is a liquid and the other one is a solid, the solid is what we call the solute because it's usually the one in the smaller amount. The solvent is the one that's doing the dissolving. The solvent is the one that's doing the dissolving, which is usually the one in the greatest amount, is usually water. And when we have water as the solvent, we call it an aqueous solution. And remember, those state of matters were solid, liquid, and gas. So now we are adding a fourth one, which is aqueous. And we just say that is AQ. So we use AQ for it. Anytime you see AQ, you know that the solvent is water. If you don't see AQ and you're dealing with a liquid, the solvent is not water. It has to be water to be called aqueous. When we're mixing things and making solutions, those solutions could be different types. They could be a gas in gas solution. It could be a solid in liquid solution. It can be a gas in liquid or solid in solid. If it is gas in gas, it's just pretty much air. If it is solid in liquid, like seawater, we can say this a homogeneous mixture. And if water is a solvent, we call it AQ. We can also have gas in a liquid, which is what you have in your soda. When you open your soda, you see all those bubbles because gas is dissolved in water. Or you can have a solid dissolved in a solid, like brass. And it's usually a melted, well, starts like a melted solution and then it solidifies. And if it is a solid in solid, the one that is the highest amount will be the solvent. The one that's the smallest amount will be the solute. Okay, so now that we have different type of solutions, let's look at the one with the solid and the liquid. So let's say you add salt to water. That salt is an ionic compound. It has charges for the sodium, charges for the chlorine. That's why it's ionic. The water has some properties associated with it that is going to try to engulf that ionic compound, breaking it apart into the sodium and the chlorine. So it's separating those ions. And that's why solids in liquids dissolve in the liquid. All this requires some energy. We are not going to look at how much energy is required for a solution to this, for a solid to dissolve in a liquid. That's for a higher level chemistry. We do that a little bit in Chem 1. All you need to know is that you put a solid in a liquid, it's going to break apart because the water molecules are going to trap, are going to separate the ions of that solid if it is an ionic compound. It doesn't happen to non-ionic compounds. It has to be ionic. And it does that because the hydrogens that tend to be partially positive charges. We're not dealing with those type of situations here. I mean, you don't need to know why that is, that hydrogen is positive. But the hydrogen, which is positive, ends in the water, get attracted to the chlorine, and then the oxygen, which are going to be negative, attract to the sodium, separating those ions. That is called solvation. As long as you know that solids in water separate because the water gets attracted to the positive and the negative of the solid ions, you are good. And that is called solvation. You are even better. You don't have to know the mechanics of it at this level. Okay? What you do need to know is that when we mix things in a liquid, sometimes they mix, sometimes they don't. If they mix, you get a homogeneous mixture. If they don't mix, you get a heterogeneous mixture. So like water and oil, they don't mix together. The oil stays together, the water stays together. You see two layers. That's why it's heterogeneous. The reason why it's two layers is because oil is non-polar and water is polar. There's two different polarities. They don't mix together, and you see the layers. If they're both polar or they're both non-polar, they will mix together, and you will only see one layer, and that will be homogeneous. So homogeneous, most likely because it's polar-polar dissolving or non-polar dissolving. Phases, because it's heterogeneous, meaning that you have a non-polar with a polar situation going on. Now, to understand why it's polar and non-polar, you need what you're going to learn at the end of the semester. So at this point, you don't know why that is, but that it happens. Again, chemistry is like pulling layers of an onion. I give you some layers at a time, and then towards the end, we try to put all those layers together so you can understand better. And still, there's going to be gaps of the information that you know that can only be answered by a higher level chemistry, which you will not have unless you go that path. So at this point, just know why we have phases when we mix things and why we don't have, and it has to do with polarity. So we say that light dissolves light. So a polar solvent will dissolve a polar solute. A polar solvent will not dissolve a non-polar solute because they're not alike. Now, when they do dissolve, you have a situation where you have a liquid and you start throwing salt in it. The salt is going to dissolve. That will be an unsaturated case because you can add more salt to it and it will still dissolve. So unsaturated conditions are pretty much diluted solutions because they don't have enough of that solute in it. As you keep adding salt to that liquid, there's going to be a point where you cannot dissolve any more salt, and you're going to start seeing the salt depositing at the bottom of that container. When that happens, as soon as that happens, we say that that solution is saturated because you cannot dissolve any more solute into it. unless I increase the temperature. If I increase temperature, I can dissolve more solid that I should be able to in normal conditions, and we call those cases supersaturated conditions, which are very unstable. A little mix will make it that solute precipitate again. Is a pretty cool thing to see happen. So when you mix solids into liquids, one of three things can happen. It will dissolve, which will be an unsaturated case where it's diluted. The more salt you add, it becomes more saturated, less diluted, until it reaches a point where you cannot dissolve anymore. That point is the saturation point. And if you increase temperature, you might be able to dissolve a little more, which is going to create a supersaturated solution because it holds more than theoretically possible. And there's some situations in which you want to do that. And you need to be able to determine which of those three situations you have happening. And there's an easy way to do that. Because we can create these graphs that are called solubility charts, where you graph the solubility versus temperature. You're going to create these lines in there. When you do that, solubility versus time increases with temperature because temperature allows for more solid to dissolve. That's why those lines are going up. And there's tons of charts that have this type of information for different type of substances. So don't think that it's only these four, 1, 2, 3, 4 in here. There's plenty of other ones that have even more. If I ask you to use this chart, you will be given the chart. If you have to use it, it's not in your reference tables right now, because depending on what I want to do with you guys in the exam, it will be provided or not. Just know these lines are usually going up because solubility increases with temperature. For most types of solutions, there's some that go down because for every rule, there's an exception. In some cases, increasing temperature makes that solubility go down instead of going up. It has to do with other factors that we are not going to explore here. Just know that you could have a chart that is going down instead of up, and that's the case. Now, by looking at the chart, there are three things I want you to be able to determine if it is saturated, unsaturated, or supersaturated. It's very easy to look. It's very easy to do. The line, any point in the line means saturated. So I can go, let's say, at a degree of 40 degrees Celsius to the first line in here for potassium nitrate is around 60 grams of solute per 100 grams of water. That's the saturation point for potassium nitrate at 40 degrees Celsius. If I give you a solubility of 20, that's a point under the graph. Points under the graph are unsaturated. So under the graph, unsaturated, on top of the line, saturated, that means anything above the line is super saturated. So for any substance, I can ask you, okay, if the solubility of this substance is X, will the solution be saturated, unsaturated, or supersaturated? All you have to do is go to the graph. So if I still use potassium nitrate and I tell you that the solubility is 80 grams per 100 grams of water, will that be supersaturated, unsaturated, or supersaturated? At 40 degrees. If I tell you it's 80 at 40, the saturation point is 60. So if it is 80, it's super saturated. So all you have to do is read the graph with a small condition that you have to be careful with. If I tell you that the solubility is per 200 grams of water, I'm telling you that is twice the amount that you have, because these lines are per 100 grams of water. So if I give you 200 grams, it's twice the amount. So you have to be careful with the units. And that's a got you moment all the time. Not anymore, because I just told you. So look at the graph. It tells you the saturation condition for that solid in a liquid. And this is only for a solid in a liquid. It doesn't apply to the other type of solutions, because now I can have a gas in a liquid. When you have a gas in a liquid, solubility doesn't increase with temperature. Solubility decreases with temperature. It does the opposite. That is something that we explore in Chem 2. We don't explain why here, but I'm going to tell you kind of anyway. When you increase the temperature, those gas particles are going to have more energy to move around, so they're not going to want to stay in the liquid. They're going to want to escape out of the liquid. And because of that, the solubility decreases. Again, that's something that we explore later on. You don't really need to know, but I just told you because I don't want to leave the room wondering why is that happening. I know, you don't care, but so solids in liquids, solubility increases with temperature. For gases, is the inverse logic, and it has to do with those molecules wanting to stay in the liquid or not. Now, why is it that when you open a soda can, the bubbles escape? That has to do with pressure. It has nothing to do with temperature. When you increase the pressure, solubility drops, causing bubbles to form and escape. Because the bubbles are escaping the liquid, that solubility goes down. At high pressure, those bubbles stay inside the liquid. They don't have anywhere to escape. So that solubility remains the same, doesn't change, whatever that might be the case. So higher pressure, higher solubility. Now, we are going to finish this topic for today talking about two things. One of them you already know how to do. The other one is new, but it's not that hard. So we have mixture, we can quantify with numbers that mixture by calculating a mass percent or calculating what we call molarity. It's a capital M. A molarity is how many moles of the solute divided by liters of solution. Mass percent is done the same way we've done already in class, which is the mass of the solute divided by the mass of the solution times 100. Just remember that mass of solution in here, because it's a whole, is the mass of the solute plus the mass of the solvent. And if I calculated a mass percent of solute, I can calculate a mass percent of the solvent, which is the difference from 100 from the mass percent of the solute. So if I have bleach, which is 6.25% sodium hypochlorite, that means I have 6.25 grams of sodium hypochlorite for 93.75 grams of water. It's a mass percent. They have to add to 100, and that percent can translate to a mass if I use 100 grams of that substance. Again, molarity is created by taking a solid, dissolving it in a very specific type of container, which is called a volumetric flask because it's calibrated to a line. When we put the solid and add the liquid and fill to the line, we get exactly whatever that flask tells you has in there. Usually, when we do these solutions, we call them stock solutions, and they're a liter of that solution. So you can calculate that molarity. One thing I don't want you to confuse, that capital M is molarity. The small m is meters. And there's another M that you don't get to see in this class, but in the next class, in Chem 2, which is called molality. We don't go over molality in here. That one is another small m. Again, so why do we have 3 letters for the 3 different things? Because we cannot make things more confusing than they already are. I'm just being sarcastic. Now, there's one more thing that is called dilutions. We are going to explore dilutions in class in the lab next week because you are going to make stock solutions out of Kool-Aid, and then you're going to dilute those solutions to other concentrations. So we'll go over the mechanics on how to do that next week in lab. So with this, we are finishing chapter 4, which was on how to do the mass percent calculations, how to do mole calculations, looking into solutions, and doing empirical and molecular formulas. Those are a lot of different type of problems. You are also going to have a study guide that has some practice problems in there for the next exam. I'm still working on those, so they're not posted yet, but they will be soon. Okay, so with this, I'm going to finish chapter